I would like now to pass to Wouter, so he introduce our last speaker for today.
Thanks, Dimitra. So 3 years ago, Dask enabled us at ASML to make a start with scaling out our existing Pandas code on our on-premise cluster. And it proved to be really valuable for us and made a case towards ASML that this is the way to go. And this led to a whole new group starting at ASML, and I'm still part of that group. So I'm happy about all the developments going on at Dask. Therefore, I'm happy to introduce to you Matthew Rocklin. He's a long-time open source developer, core maintainer of Dask, and founder of Coiled. He will talk about Dask at global scale with Coiled. And the floor is yours.
Yeah, hi everyone. Thank you so much for the chance to say hi. I won't keep you from Matt's talk. I know that's what you're wanting to hear, but we just want to thank you for your support of NumFOCUS and of the whole ecosystem. We're excited that this is the second online PyData event in the Netherlands. The first one was a big success, and this one looks like it is following that path. I'd just like to invite everyone to learn more about the work we're doing at NumFOCUS on our website. You can tune into social media or subscribe to our newsletter. So again, thank you so much for helping us with our mission to support the projects that you use and you're depending on. Matt, we'll let you take it. And
yeah, so hi everyone. My name is Matt. Let me bring up my slides here. I also put a link to the slides in the Discord. So hopefully you're now seeing Coiled, Dask everywhere. So a bit about me. My name is Matt. I'm a longtime maintainer of various open source projects in the Python space. I mostly think about parallel computing, mostly with a project called Dask, which we're going to talk about today. Recently, some of the Dask maintainers left and made a company. We're trying to make it easy to deploy Dask. And this talk is to talk a little bit about some of the motivations for that, mostly around solving sort of some IT needs that we saw. So this talk is sort of blend nonprofit, for-profit, open source infrastructure topics. So the context of this talk, I usually think of the context where we want to rapidly explore data, and that's really what PyData, I think, shines at. You have a bunch of information that's being presented to you, and you want to derive some value from that. You might use NumPy, Pandas, scikit-learn, PyTorch, XGBoost, Jupyter, plotting libraries, et cetera, to do that. And hopefully that works out really well for you. Sometimes the data that you are given is large, or the computations you want to do are time-consuming. So sometimes you want to scale. This can be hard because programming many computers is harder than programming a single computer. Oftentimes, people who are taught to do statistics are not taught to do network programming. It can also be hard because it's hard to operate on computers that we don't control ourselves. This creates lots of administrative issues. The first set of these problems, programming many computers, is why we made Dask. Dask makes it easy to operate on many computers at once in a way that's hopefully comfortable and familiar to you. What we found after many years of using Dask is that there was another set of challenges, these IT challenges, and that's why we made Coiled, to solve the IT challenges. So in this talk, we're going to talk first a little bit about Dask and what that provides. Then we'll talk about what we often see in practice, but why it's kind of hard to use tools like Dask. And it'll give some motivation for Coiled, and hopefully at the end I'll say, hey, there's a public service you can go use, which you might find interesting. But our goal here is to make computing generally more accessible. And this could be for people working in very large companies of very intense IT constraints, or it could also be for individual students who want to play around or learn a little bit about parallel computing, but don't necessarily have access to an IT department or a DevOps team to help them set up those resources. So I'm going to switch to a quick example first. So let's try this. So I am on my laptop here on the left. I've got an IPython session open, and I'm going to connect to a cluster of machines that I've allocated beforehand. And I might, let's run a simple computation. Let's maybe make a function inc. which will import time and random. We'll sleep for a random amount of time, and then return x plus 1. So this is just sort of a simple dummy function that I could run locally on my laptop. And it sleeps for some amount of time and then returns a number. You might imagine this being some other function that you're thinking of. Load some data, maybe train some data. And maybe I want to run this 1,000 times. And so I can use Dask to leverage a bunch of machines that are somewhere else to do that work for me. And we're seeing that activity happen on the right. Every little green rectangle that appears on the right is some remote call of increment. And so now we have all of those results. So Dask is very much about presenting the illusion that all of these remote machines are actually just kind of on my local machine. Here I'm using sort of a very basic map interface for Dask. There's lots of other libraries that are built around Dask. For example, Dask is integration with pandas. So I'll go ahead and load up some data that's sitting on Amazon S3. This is a New York City taxi cab data set. I think it's maybe 20 or 30 gigabytes of RAM. You can see the memory increasing up here in the upper right. And now we're loading that data, again, not on my single machine, but on many machines that happen to be living also on Amazon. And so we're getting this experience of using pandas-like computations, but now that work is being spread out to lots of other machines that are living elsewhere. And in principle, in theory, Dask should look very much like APIs that you're familiar using with today in the sort of PyData ecosystem. But in practice, there's a lot of internals that are working to make it so that that's easy to do. So we might, compute maybe the average trip distance based on passenger count, and we find some result. And so there's again lots of activity happening here on the right for all these distributed machines. But on the left, we get to act like data scientists and write code that is hopefully interpretable to most people in the audience. So that's what Dask provides. Let me switch back to slides for a second. So let's talk about Dask for a moment, and we'll get into what was challenging to make all of that work smoothly. So Dask is a library. It's a Python library that was designed to scale other Python libraries in the PyData ecosystem. It works well on your laptop for multi-core and larger-than-memory execution. So if you've got 100 gigabytes of data and you just want to sort of stream through that on your laptop, Dask would be a very good fit. Dask is also designed to operate on clusters and machines. So if you have 1,000 machines on some research scientific cluster or on some Kubernetes cluster or on the cloud, Dask can help you leverage those machines, and that's what we just saw. Dask is easy to use, we think. It's relatively lightweight. It's pure Python, and that has led to a lot of integration with other Python libraries. So again, Dask was originally designed to scale libraries like NumPy, Pandas, and scikit-learn. When we were making it, we thought, these libraries are good, but they don't scale very well. You can't use Pandas on a terabyte of data. And so we built variants of those libraries which wrap around the existing libraries. So if you use Dask Array, you're using many NumPy arrays in parallel. If you use Dask Data Frame, you're using many Pandas data frames in parallel. Using Dask ML, you're doing some fancy machine learning stuff. But these libraries are very much tightly coupled with their single machine counterparts. In order to make those sort of parallel NumPy, parallel Pandas libraries, we ended up having to build a dynamic task scheduler. So Dask works kind of in these three stages. On the left, we have Pandas-like code or NumPy-like code, which is, again, hopefully interpretable to you. Dask translates that into a task graph. Let me actually switch back to our demonstration here for a second, and maybe we can go and look at what those graphs look like. So when I write something like this group by computation, what's actually happening is that Dask takes that computation, it breaks it down into lots of little small tasks that depend on each other. Then you maybe didn't see it, it was a little bit too fast, but then executes all those little small tasks on the various machines that we have. Right, so I've got here 10 machines, each with 4 cores sitting on the cloud. And so what we found is that many users wanted this sort of graph execution engine, but didn't necessarily want the pandas interface or the NumPy interface. And so they took just the graph execution and ran with that instead. So again, Dask is both a set of high-level APIs and an internal low-level task scheduler. So maybe sort of like the engine, the task is kind of like the engine of Dask that executes all of these tasks in parallel on different machines. It was as though we had built a fast car, and people said, that's a really nice car, but I actually just want the engine. And that's because they were doing something else. Python people were building rockets or Roombas or other devices. And so people in Python tend to be very creative, and they have lots of different needs. It was actually really hard for us as a Dask community to make high-level APIs that would fit all those different needs. People had lots of different constraints. And that was actually really exciting. And that has resulted in lots of different libraries adopting Dask. So if you use libraries like NumPy or Pandas, yes, Dask has integration, but also Scikit-Image or XGBoost or Rapids or Xarray or Prefect. There are many libraries that are now integrating with Dask. We're seeing some of those examples on the right. So here we're seeing, looking at ocean currents off the coast of Japan in real time. So this is the same scalability that we would get with the parallel pandas interface, but now with a very different kind of data. Dask is used in point-and-click applications, like Napari, a 3D image viewer. So this isn't targeting data scientists, this is targeting actual scientists who are sitting at a lab bench somewhere. Projects like Data Shader for advanced visualization use Dask, along with other libraries like Numba. And so what we're seeing here is a variety of different applications that we did not anticipate that are all powered by Dask, which really extend a lot of the reach. Dask is fully real time. And again, projects like Prefect or Rapids are also now sort of built on top of Dask, which makes it really exciting. So we started with this application of big pandas, big NumPy, but we found that the community took Dask in very different directions from what we anticipated. A lot of people build on top of it, and that's sort of where we see a lot of Dask growth today. So, unfortunately, even though Dask had succeeded in parallelizing a lot of computations, we still saw a lot of groups, a lot of individuals struggled to adopt it for reasons that had nothing to do with parallel computing. If you wanted to use Dask today, you might look at our docs and you'd say, great, I'm gonna go get some cloud account, learn how Kubernetes works. I need to figure out how to access my data. Maybe I have data in a private S3 bucket. How do I move around my credentials to all of my Dask workers? Or I want to run some special library. Maybe I'm using the Facebook Profit library, for example. How do I install that not on my local laptop, but on 1,000 computers in the cloud? And so there's lots of other challenges that we found people had to figure out before they could get the sort of the easy experience that we wanted people to have. Now, the sharp people who could do this eventually succeeded, and everything was great, and they were very, very happy for a while. But generally speaking, if you have used Dask on more than your laptop, you've had to answer some of these questions. And these questions end up not being things that we teach your sort of average data scientist. You don't sort of learn how to use Kubernetes in your statistics course. And so there's this other skill set that we found a lot of people struggling with. Additionally, once people did succeed in getting these skills, there were a different set of concerns that occurred. So things like they left their cluster on accidentally and were charged $10,000 to their company accidentally. IT suddenly gets involved. They say, wait, what is this Dask thing? It's running on our computers. What's it doing? They learn that it's running arbitrary Python code across their network and isn't secured by default. And they understandably have some concerns. The manager is concerned a little bit about how we're spending money. And so there's lots of other challenges that end up arising once you get past the sort of early adopter stage in a company or in an academic setting. Also, we found that a lot of these sort of early adopters who were originally data scientists, but ended up becoming this IT data science hybrid, they ended up spending a lot more time on their IT work than they wanted to, and they wanted to get back to data science. They wanted to sort of remove the need of managing these systems from themselves. And so in general, Dask solved the computational problems, but the organizational and IT problems still persisted. A good example of this is the Pangeo project. Pangeo is a collaboration of earth scientists who are doing things like climate change, hydrology, coastal erosion. It's an international group, and they started off as lots of earth scientists coupled with some open source developers. And they made a really awesome stack with Jupyter Hub and Dask and Kubernetes in the cloud. And it was amazing. We really changed, I think, how a lot of these climate scientists and meteorologists do their work. What we found pretty quickly, there were all these other problems that we've already sort of talked about. Building Docker images, managing data access, handling user quotas. Also things like, what if maybe you have some group that's managing the Kubernetes cluster in the United States, but you've got, some EU weather service that wants to read their data, and they don't want to sort of always cross the Atlantic in doing that data transfer. Or maybe their data isn't on AWS, maybe it's on Azure. And so there are lots of other challenges that we found after sort of digging in a little bit deeper. There were also a lot of social concerns. It was hard to find people to keep things running. Just having, a dedicated DevOps person around ends up being a pretty critical part of any service like this. This also wasn't very accessible for smaller groups like individual researchers or professors or students. And so we wanted to find some way of replicating the Pangeo stack, but that could be applied to lots of other disciplines and lots of other groups. So earlier this year, a few Dask maintainers and some web developers made a small company, Coiled, which our tagline is Dask for everyone, everywhere. And we are trying very hard to make it as easy as possible to solve those IT and DevOps challenges so that people can do all of this great work with Dask on data science and machine learning workloads. Here's what I'll put on my for-profit hat just for a moment. Hopefully you guys don't mind. So Coiled provides hosted Dask. It manages software environments, it manages teams. It's fully secure. It also runs from anywhere. So it's designed to reduce IT barriers. We've tried very, very hard. It's a lower right of the screen. There's a pip install command and then 2 Python commands. And if you run those, you'll get a Dask cluster on Amazon. You'll be asked to authenticate with GitHub or Google and provide some token. But anybody, if you want to, can run this now. And it's free to use and relatively easy. That's also what I was using when I first started my talk here. Let's go up to the very top. So on my laptop, I asked for a cluster of 10 machines. And that's how I started. So you can actually do everything that I did here in the next couple of minutes if you're interested in doing that. Let's see. I've got around 5 minutes left. I'm going to, I think, skip some examples. What I will do is I'm going to point you to docs.coiled.io, which has some examples that you can run pretty comfortably. And again, this is maybe a good way of playing around. So I was going to show you scaling XGBoost, and if you want to, you can go launch a notebook and play around in a minute or two. I was also going to show you Prefect, which is intentionally not a notebook. Prefect is like an Airflow alternative. There's a script here you can run, which will run some small job for you, but integrating with Prefect. So this shows you how you can use Dask and Coiled to scale up lots of popular libraries, again, like XGBoost, Prefect, PyTorch, etc. but now maybe a little bit easier because you don't have to figure out how Kubernetes works or how the cloud works. So let's dive in a little bit into how Coiled solves these problems in particular. And actually, I'm going to switch back to the demonstration just for a second. And there's a lot of things that happened here that I want to sort of call your attention to. So when I asked for a cluster, some service went off and allocated a bunch of machines for me in the cloud. Then it set up security on those machines. It installed software on those machines. So things like pandas were available on those machines for me, or libraries to read from S3. And then it secured it and gave me access to that. And so a lot of magic happened in these two lines. Second, when I'm accessing this data on S3, I actually need to be credentialized to access this data. Amazon will not let just anybody access it. They need to know that you're a person who has an Amazon account. And so Coiled got my local credentials, forwarded them in a very secure way to my remote workers, and made those workers look like me. So passing out authentication is really critical. Also, if I try to do something like I try to scale my cluster out to 1,000 workers, Coiled is going to say no. Your account can't use that amount of work. You're already using 42 cores. Your account is limited to 200. Sorry, I can't give you 4,000 more cores. So these are the sorts of capabilities that are happening in the background that end up being pretty critical. So I'm just going to blast through a few of these in the next few minutes. So Coiled runs on AWS currently. We're launching Azure in the next probably month or so. And it runs on any region, on any account. So you can provide your own AWS credentials if you work in a more secure environment, or you can use ours. It runs on any region. So anywhere AWS runs, we run. We run sort of at full scale. Coiled builds software for you. This was a really common challenge we found with the Pangeo community, is that every different scientist had a different set of libraries that they wanted to use. And so rather than us managing and building Docker images for them, it ends up being very, very helpful to give everybody the capability of making these things themselves, even if they don't know how Docker works. Additionally, having some shareability of those software environments ends up being really important. What we found often is that groups like team leads, like professors, would often make a software environment for their group and then want to share that among their group. And so having some basic sharing ability ends up being pretty critical. One of the things we really cared about when making Coiled was not forcing people into our development environment. If you look at competitors like Databricks, you sort of always have to use Databricks inside of Databricks notebooks. It turns out the Python people tend to use IDEs sometimes, like VS Code or PyCharm, or they use things that are not notebooks. We saw in the video earlier Napari, an image viewer, and that's not a notebook application. That's actually like a rich client application that has to be run on a desktop. And so we wanted Coiled to be able to run from anywhere. And so in our demonstration, I'm running this from a local IPython session. I could have run this from a local Jupyter notebook. I could have used a notebook in the cloud. I could have used some other notebook service like SageMaker. And so Coiled is very much intentionally decoupled from where you run your execution. We're doing this intentionally because we found it very difficult to try to fully encapsulate everyone's development environment. It ends up being tricky. Everyone has their own preferences for how to build their own workspace. Cost management, we saw this before. Coiled manages costs. We track every CPU second everyone runs. And that allows people who are controlling budget to be able to specify different policies, which also ends up being useful when you are supporting a lot of sort of novice users that might leave clusters on for a long time, or might ask for GPUs but not use them. So having those sorts of policies in place ends up being very useful. Coiled can launch GPUs by default. It also critically includes a lot of pre-configured software environments. Configuring GPU software environments ends up being very hard. And so if you want to try out some of the newer libraries like Rapids or PyTorch or XGBoost, GPU accelerated, Coiled is an easy place to do that experimentation. I gave a talk, actually, I think just yesterday at NVIDIA GTC, where I sort of talk about using Coiled to switch back and forth between CPU and GPU architectures with the same code. Coiled is fully secure. So again, you can run things inside of your own account. We do end-to-end network security, and we're doing all the same best practices you'd expect. Data is stored at rest in an encrypted way. So I'll finish up here. Dask and Coiled are trying to let us pretend that our cluster is like a laptop. We're trying very much to replicate that same experience of working locally, but on many machines. That's a lie. You definitely need to understand how distributed computing works in order to be fully efficient, but we're getting a lot closer, and we're working really hard to remove some of those barriers. Again, Dask solves lots of the programming challenges and a lot of the algorithmic challenges. And Coiled, we're now trying to solve a lot of the IT or organizational challenges. So that's it. If you want to learn more, I recommend dask.org for information around Dask, coiled.io for information about Coiled. And if you're interested in trying out all of this stuff, everything I've done here is publicly accessible. If you pip install Coiled and then create a Coiled cluster, you'll be ready to go. So that's it. Thank you everyone for your time. And I'm open for questions.
Yeah, thanks for this talk about these developments around Dask. We have a question from Ruben Mak. Besides the non-computing challenges, what are still open challenges in the computing field for Dask? What are operations, applications, and algorithms that are still hard to run compute distributed?
Yeah, I mean, there's like a technical answer to that, which is there's lots of operations which is hard to parallelize. You know, a simple one might be something like median, for example. It's hard to compute the median in parallel. There's alternatives like approximate quantile, but there's lots of algorithms that are just hard to do. I would say I'm going to answer that question slightly differently and say that there's a social challenge. I think right now what we're seeing is many groups adopt Dask, but Dask ends up being not the right library for, a climate scientist to use, for example. And so what we see is a lot of other libraries building APIs and a lot of functionality around Dask. And that's, I think, where we're seeing a lot of growth. And so libraries like maybe Xarray and Pangeo have done a good job to translate Dask for a certain set of scientific or business users. And we're seeing a lot of maybe horizontal growth. So for example, right now in life sciences, there's a lot of packages which are now starting to build Dask support. And so I think the next step in sort of expanding use is not about solving harder algorithms, it's just in solving more cultural or community challenges, which often is done with people like the PyData community building libraries around Dask or integrating Dask into their libraries.
Okay, thanks. We have another question from Akshar. Apart from bringing Dask to cloud, what unique features do you have that's different from Databricks? And how much do you plan on serverless philosophies in future? Or do you still want your customers to maintain their clusters on cloud?
Yeah, that's a good question. In regards to Databricks, the main differentiation, I think, is just that it's based around Dask. So most people who are using Coiled today, like Dask, they want something kind of like Databricks on the cloud. And so Coiled ends up being a nice fit. I think the sort of separation of running Coiled not necessarily in Databricks notebooks opens up lots of other possibilities that ends up making it a little bit more easy to integrate. I think Databricks sort of tries to own your world, and Coiled is just sort of solving one problem of solving distributed computing at scale. In terms of serverless, people mean different things when they say serverless. But here, I'm asking for a cluster. And this cluster, I'm asking for a number of workers. So I'm bringing in some concept of what a server is, but I'm not thinking about how to allocate or provision servers. Additionally, you may notice the warning here, this takes about a minute. And so there's about a minute spin up time, about a minute delay whenever I want to add or remove machines. This is about as fast as we can make things without making it more expensive. But there are things that we could do to give you, machines on the fly where you stop thinking about it. It would just be a bit more expensive. And we're sort of playing with that a little bit. Systems like Lambda, which is maybe the more like traditional serverless approach, end up being awkward for two reasons. One, they're much more expensive. Lambda has like a 10x cost boost over spot instances on AWS. Also, systems like Lambda don't handle internode communication. So this graph on the right, some of these tasks require information from other tasks. And systems like Lambda sort of don't manage state well enough. And so they're not appropriate for a lot of data science workloads. Hopefully in the future, we do find some system that lets us do that, but we're not there yet.
Okay, thanks. There are two more questions, but due to time, we will put them in Discord. Then that's the end of today, right? So thank you for listening in, and see you tomorrow or the day after.
Thanks for having me, everyone.
Bye.
Bye.